Hello everyone, my name is Vasilis Kontonis and this is Learning Halfspaces with Massart noise under structured distributions. This is joint work with Ilias Diakonikolas, my advisor Christos Tzamos and Nikos Zarifis. So, learning linear classifiers is a well-known problem in machine learning. We're given labeled data, for example spam and non-spam emails, and we want to find a good linear classifier. The problem is that usually there is label noise in the data. This means that some non-spam emails are incorrectly labeled as spam and vice versa. We still want to find the best possible linear classifier for this dataset, even though it's not perfectly separable by a line. So this takes us to the well-known Agnostic PAC Learning setting. So in this setting, we're given IID data, xi and yi. So xi is the data point and yi is the label. And we want to find a linear classifier h such that the classification error of h is smaller than opt plus epsilon. So opt is the minimum classification error achieved by linear classifiers. So another way to think about this problem is that you start with a perfectly separable dataset. So you start with a dataset that is separable by a line or a half space, and then some adversary picks an opt fraction of the data points and flips their labels. So this is a nice, strong noise model, but unfortunately, it's also computationally hard. So in the distribution-free setting, so this is when the underlying distribution is assumed to be arbitrary, there are many results that show that this is a computationally hard problem. However, even in the distribution-specific setting, so now we assume that the distribution has some nice structure, so for example, it's a Gaussian distribution, there are also results that show that super polynomial time is needed. So, in short, adversarial label noise is hard. So this motivates milder noise models. So one such model is the random classification noise model. In this model, we assume that the label of its point is flipped with some probability eta. So this is a pretty weak model because the assumption that every label is flipped with the same probability is too symmetric in some sense. So another model that is much more interesting than the random classification noise model, but still easier than the adversarial label noise, is the Massart or bounded noise model. So now the assumption is that the label of point x is flipped with some probability eta of x. So the only thing that we know now is an upper bound eta on this function eta of x. So now this problem becomes harder as this upper bound eta gets closer to 1/2, or equivalently as this noise rate beta gets closer to 0. So now the crucial difference between this model and the random classification noise model is that the flip probability depends on the specific point x. It's not the same for everyone. And this is what makes this problem, model much more interesting. So we start with a half space, and then we flip the labels of the points with probability eta of x. The goal is the same as before. We want to find a linear classifier that has error opt plus epsilon. Now, the sample complexity of this problem is well understood. It's d, which is the VC dimension of the class of half spaces, times the minimum of 1/epsilon squared, which corresponds to the standard agnostic learning convergence rate, and 1/epsilon times the noise rate beta. So in particular, the problem is indeed harder as the noise rate goes to 0, but it can never exceed the sample complexity of agnostic learning. So the question is whether computationally this problem is easy. So in particular, in the distribution-free setting, the major breakthrough in this Massart noise model was from Diakonikolas, and Tzamos in NeurIPS 2019, where they gave a polynomial time algorithm that achieves error eta plus epsilon. So this was the first time in many years that actual progress was made in this Massart noise model. And the question is whether this error guarantee that they get is the same as getting opt plus epsilon. And the answer is no. So opt is equal to the expectation of eta of x. So this is because you flip the label of each point with probability eta of x, you take the average, the optimal half space will have error equal to the expectation of eta of x. And this expectation of eta of x can be much, much smaller than eta. So this is far from opt plus epsilon, but they also give some strong evidence that getting opt plus epsilon in the distribution-free setting is unlikely. So this takes us to the distribution-specific setting. So now the assumption is that the underlying distribution has some nice structure. So for example, is uniform over the sphere or Gaussian, and we still want to get error opt plus epsilon. So there are many works that handle the problem when the distribution is uniform on the sphere and get polynomial dependence on the dimension, on the noise rate, and the accuracy parameter epsilon. But this is for this specific distribution. For the general class of log-concave distributions, the best known results are from Wasti, Balkan, Haktalab, and Urner in 2016, where they solved this problem, but their algorithm has a doubly exponential dependence on the noise rate. So this makes this approach non-practical even for very mild noise. So the main open problem in this direction is whether we can get a polynomial time algorithm for log-concave marginals. So log-concave distributions are a general class that includes Gaussian, uniform on the sphere, etc. So in this work, we resolve this open question and give an algorithm that has polynomial dependence in all these parameters. In fact, we solve an even more general problem. We assume the distribution to be well-behaved. So we have some assumptions, some natural assumptions that are satisfied by a large set of distributions. In particular, we call a distribution well-behaved if it's isotropic, and every two-dimensional projection has some concentration. So this means that the probability that x is very large is small, some anti-concentration, which means that the two-dimensional density of any point is upper bounded by some constant, and some anti-concentration, which means that the density function is lower bounded by some constant for all x's inside some ball. So under these assumptions, we give an algorithm that has sample complexity d over epsilon to the 4 times a polynomial dependence on the noise rate, and runs in time polynomial in the number of samples, and learns a half space with error opt plus epsilon under any well-behaved distribution. So let's see what this means. For Gaussian, we get d over epsilon to the 4 times a polynomial factor of the noise rate. But more importantly, for the general class of log-concave distributions, we get the same sample complexity, d over epsilon to the 4 times a polynomial factor. So observe that our dependence on the dimension d is optimal. So we also remark that our result can also handle distributions that have heavy tails, such as S-concave distributions, but then the sample complexity is a larger polynomial of 1 over epsilon. So let's see now how our algorithm roughly works. Ideally, one would like to minimize the 0-1 loss. So this corresponds to the standard empirical risk minimization procedure. And unfortunately, this is a hard problem. So what we do in this work is that we replace the step function with a logistic function. So we use this smooth surrogate of the step function, and we're also restricting the hypothesis, the half spaces, to be on the unit sphere. So W here is the normal vector to the half space. So we define this objective function as a function of W, and we restrict W to lie on the unit sphere. So here's what the picture looks like. So the red curve is the step function, and the blue curve is the logistic function. So as you can see, the logistic function looks like the step function, and in particular, we have this parameter sigma. So if we tune sigma to be close to 0, the logistic function looks more like the step function. So the limit of the logistic function as sigma goes to 0 is the step function. So now the approach is to do stochastic gradient descent on this smooth non-convex surrogate of the 0-1 loss. So, okay, we started from the step function and we made it smooth, so that's good, but still this is a non-convex objective, so we cannot hope to find the global minimum of this thing. The main result of our work shows that we actually do not need to find the global minimum. So we prove that any stationary point of this objective is good enough. And this is exactly what stochastic gradient descent gives us. It will give us just a stationary point. So here's the theorem. We say that there is some small enough parameter sigma such that every half space that has large angle, that is angle smaller than larger than epsilon with the optimal half space W star, will also have large gradient. So this means that all the bad hypotheses, all half spaces that are far from the optimal, will also have large gradients. So this rules them out from being stationary points of this objective. So let's see why this is true, and let's focus on a two-dimensional version of the problem. And let's also assume that the underlying distribution is uniform over the unit ball. In fact, this is very close to having any low concave distribution. So we start with our optimal half space. It's the green half space here, W star. And we also have our bad hypothesis W. So the assumption is that the angle between W and W star is large. So now the goal is to show that the gradient of this objective on W is also large, ruling out the W from being a stationary point. So since we're optimizing over the unit sphere, the gradient of W is perpendicular to W. So there is no radial component. So here, this is what the gradient looks like. And our goal is to show that this is indeed a large vector. So as you're doing stochastic gradient descent, you sample a point x, and then you update according to the gradient of that point. And there are two kinds of points. We have the blue points, whose gradients point to the left. So these are the good guys. They're going to turn W towards W star. And we also have the red points, whose gradients point to the right. So these are the bad guys. They're going to turn W away from W star. And the issue is that there could be some cancellation between these two gradient components. So since the distribution is uniform over the unit ball, you might believe that the contribution of the blue points is much larger than the contribution of the red points. But this is not true. And the reason is that we have noise. So the noise cancels out a large factor of the good contribution. So it multiplies the contribution of the blue points by a factor of beta. So it could happen that the blue part and the red part of the gradient cancel out, and you have very small gradient on W, and this would make W be an approximate stationary point. So this is what we want to avoid. So how to fix this problem now? So the way to fix this is by using this parameter sigma. So let's see how sigma works. By picking small values of sigma, we actually increase the contribution of the points that are close to the half space. So this is what it roughly looks like. Points that are inside some band of size sigma will have a large contribution to the gradient, and everything that is far away from the current half space from W will have a roughly zero gradient. So as you can see, as you're making sigma smaller, the ratio of the blue area over the red area becomes larger. So eventually, the blue guys will win, and you will have a non-trivial component to the gradient. So you will have large gradients. And this is exactly what we wanted. So we started with a bad guess, and we saw that if you pick sigma to be small enough, this objective will also have large gradient. So we can safely optimize this objective using stochastic gradient descent and return an approximate stationary point. This structural result guarantees that this will be a good half space. So I would like now to conclude with a summary of the results. So in this work, we give the first polynomial time algorithm for low concave marginals. And perhaps more importantly, we give an algorithm that is very simple. So we saw that black box stochastic gradient descent on a non-convex objective works. So there are also many interesting problems for future work. In particular, there are harder noise models that are still easier than adversarial noise. For example, Tsibakov noise model. And it would be very interesting to understand whether there are polynomial time algorithms for learning half spaces under these harder noise models. Thank you.